Hello everyone, welcome to our discussion on normalization. In this video, we are going to discuss about the first normal form and the second normal form of a relation. Now, what is a normalization? We know that to overcome the update anomalies, we should decompose a bigger schema into a smaller schema. Now, how we are going to decompose that schemas into smaller schemas? That the process is basically normalization. So normalization is the process of decomposition of a bigger schema into some smaller schemas depending on the functional dependency and the keys. What kind of keys? The super key, the candidate key, and the primary key. When we are normalizing a relation into smaller relations, then we should focus on three things. First one is the attribute preservation. What is attribute preservation? It says that if there are x numbers of different attributes present in this bigger schema, there should be x numbers of different attributes present in the smaller schemas also. No, we cannot exclude any attribute or we cannot include any attribute in the smaller schemas. The second one is the lossless. This is a very important aspect when we are performing decomposition. Lossless means that if we decompose a bigger schema into a smaller schemas, now if we perform joining of the smaller schemas, then we should get the exact bigger schema. No new tuple will be added or no tuple will be discarded from the actual bigger schema. So we have to ensure that schemas are lossless. And dependency preserving means the dependency present in the bigger schema, the actual schema, should be present in some form in the smaller schemas. Let us discuss about the different normal forms are available. There are 5 types of normal form are available. The first normal form, it deals with the multi-valued and the composite attribute. And 1NF, we do not allow any multi-valued or the composite attribute to be present in a relation. In the second normal form, it deals with the partial functional dependency. We are going to learn more about partial functional dependency later. In the third normal form, it deals with the transitive functional dependency. Transitive functional dependency means those functional dependencies which follows the transitive inference rules of the Armstrong axioms. Now, in case the fourth one is the Boy's code normal form or the BCNF. It ensures only one possible primary key for a relation. The fourth normal form deals with multi-valued dependency, and the fifth normal form is also known as the project joint normal form or PJNF. It depends on the multi-valued functional dependencies as well as joining of the smaller schemas will give you the exact bigger schema which we have dealing in initially. So let us discuss about the first normal form. In a simple way, we can say that the first normal form, every tuple must contain exactly one value of each attribute from the domain of the attribute. Means multi-valued and composite and their combination are not allowed in 1NF. So multi-valued composite or the combination of multi-valued and composite attributes are not allowed in 1NF. So if we go by the definition, then a relation R is said to be in 1NF if and only if the domain of all attributes of R are atomic. Atomic means a single value. So at a junction of a row and any column, there must be only one value. If there is multiple value, then we are going to say that it is not in 1NF. So let us take the example student contact. Here you can see that the base table or student contact table have three attributes: roll number, name, and phone number, where the roll number is the primary key. Now, you can see that phone number is a multi-valued attribute. So, to be in 1NF, we cannot allow any multi-valued attribute to be present. So, this table need to be decomposed to make sure that it is in 1NF. Now, how we can decompose this table? This step is actually done in when you are going to convert the ER diagram to the relational schema. So this is handled over there. So how we can handle this? First, we take out the single valued attributes. So roll number and name will be stored in one relation, and the contact, which is the multi-valued attribute, for each and every contact of a person, one row will be added. So you can see that the rule number 2 having two contacts. So for each and every contact of phone number, a row will be present, and in this relation the roll number along with the phone number will make my composite primary key. So in this way we can convert schema which is not in 1NF into a schema which is in 1NF. Now after that comes the 2NF. 2NF is based on the concept of fully functional dependency and the prime attribute. So let us understand the full functional dependency first, then we are going to discuss about the prime attribute. Let A and B are two sets of attribute in relation R where the functional dependency A determines B holds. So A is a set of attribute, B is also a set of attribute, means there are multiple attribute can be present in A and B. If removing any attribute from A, so as A have multiple attribute, we can remove one attribute from A, destroy the functional dependency A determines B, means if A, B does not hold anymore, if we remove a single attribute from A, then we call A determines B as a full functional dependency. Else, it will be called a partial functional dependency. So let us take an example. Consider that R is a relation of four attributes W, X, Y and Z where the set of functional dependency FD is given by Wx determines YZ and X determines Z. So we can write Wx determines Y using decomposition rule. Then Wx determines Z using the same decomposition rule, and X determines Z. Now you can see that if this is my A and this is my B, according to the definition of full functional dependency, A determines B will be B is fully functionally dependent on A. If we remove any attribute from A, this relation will not hold. This functional dependency will not hold. So here my WD is X, so Wx determines Z. Here if we remove W from it, still the functional dependency holds, right? So this is not a full functional dependency. So this functional dependency is partial functional dependency. But here if we remove W, this X determines Y does not hold. So and similarly if we remove X, then W determines Y does not hold. So this is a full functional dependency. Similarly here there is only one attribute in the left hand side, so it is also a full functional dependency. Let us take another example. Suppose R is a relation of A, B, C and D and E, and the functional dependency set F is given by AB determines C, C determines D and D determines E. Here the functional dependency AB determines C. If we remove A, that functional dependency does not hold. If we remove B, then B determines C, that functional dependency does not hold. So here each and every functional dependency is full functional dependency. Let us take another example where my relation is R is on A, B, C, D, E, and here the functional dependency set F is given by AB determines C, B determines CD, and D determines E. here you can see that using these two functional dependency, we can say that AB determines C and B determines C. Here we have used the decomposition rule of the functional inference of the functional dependency. So here if we remove A from this relation, still the functional dependency B determines C holds true. So this functional dependency is partial functional dependency. It is not a full functional dependency. So this is the concept of full functional dependency and partial functional dependency. So let us discuss about the partial prime attribute. Attribute A in relation R is said to be prime attribute if A is a part of any candidate key of R, else it is a non-prime attribute. So let us take our previous example. First we have to determine the candidate key of the relation R. Relation R is of attribute W, X, Y and Z, and the functional dependency is given. The simplest way to find the candidate key is to find the essential attributes. What are the essential attributes? Essential attributes are those attributes which cannot be determined by any other attribute. So essential attribute in this relation is, you can see that W and X, these two attributes are not present in the right side of the functional dependency. So those two attributes cannot be determined by any other attributes. Now, if we identify the essential attribute, we can definitely say that those attributes will be present in the candidate key. Now, so we start with the closure of the essential attribute. So Wx closure, here we are getting Wx, Y and Z. So Wx closure is giving me all the attributes in the relation R. So we can say that for the relation R, my candidate key will be W and X. Now, as the definition of a prime attributes is that it will be an attribute present in the candidate key. So we can definitely say that the prime attribute for these relations are W and X. Similarly, the non-prime attributes are Y and Z. R is a relation of A, B, C, D and E, where the functional dependency is given by AB determines C, C determines D and D determines E. So here the essential attribute is AB. So because we cannot determine any AB from any other attribute. So as AB is my essential attribute, we will start analyzing with AB closure of A and B. So from here we can see that from AB we are going to get A, B and C for this functional dependency, and if we get C then we are going to get D also, and if we get D then we are going to get E also. So AB closure is giving me all the attributes. So here my candidate key will be AB and my prime attributes will be A, B and non-prime attributes will be C, D and E. Right? Now let us take, if for the same relation my functional dependency is given by AB determines C, B determines CD and D determines E. Here the essential attributes will be, you can see that we cannot determine A or B by any other attribute. So essential attribute will be AB and AB closure will be AB determines C as B determines CD. So we can write AB determines C and D also. As D determines E, so E will be in the closure of AB. So here from this one we can say that the candidate key will be AB and the prime attributes are A and B and the non-prime attributes are C, D and E. So in this way we are going to determine the candidate key and the prime and the non-prime attribute. We are going to see some more example of this when we are going to discuss the second normal form of the 2NF. So let us go to the definition of the second normal form. By these normal forms are proposed by the EF courts, and by the EF courts definition, a relation R is said to be in 2NF if it is in 1NF. So there should be no multivalued or the composite or the combination of these two attributes in the relation, and every non-prime attribute in R is fully functionally dependent on the primary key of R. Now here the definition is complete, but the problem is that as we know that in a relation there can be multiple candidate key, and depending on the DPA he or she can choose any one of the candidate key as the primary key. So which primary key is going to the DBA choose, that is depend on the DBA, and that is why the analyzing a relation depending on the primary key is little bit difficult. So the generalized definition of the 2NF, it says that a relation R is said to be in 2NF if it is in 1NF like previous, and every non-prime attribute in R is fully functionally dependent on any candidate key of R, right? So here the general definition remove the primary key term by the candidate key. So we need to consider each analyze. So while analyzing the 2NF, we need to consider each and every candidate key. So let us discuss the 2NF with some examples. So the first example is R is a relation of W, X, Y and Z, where the functional dependency is given Wx determines Yz and X determines Z. Here we have already seen that the prime candidate key is Wx and the prime attribute should be W and X, and the non-prime attribute are Y and Z. So here the functional dependency, I have written them in the decomposed form for your better understanding. You can see that this is a fully functional dependency because removing W or removing X from this functional dependency, the functional dependency will not hold. But here if we remove W from this relation, this functional dependency, still X determines Z, that functional dependency holds. So this is a partial functional dependency. Now as Z is a non-prime attribute, so by definition of 2NF, it says that each and every non-prime attribute should be fully functionally dependent on the primary on the candidate key. So you can see that Z is not fully functionally dependent on the candidate key, that is Wx. So this relation R is not in 2NF. So we need to make it in 2NF. So the 2NF we need to decompose the R such a way, we need to decompose R in such a way that it will be in 2NF. So how can we do that? The first thing you are going to create the relation is from using the candidate key. So what are the candidate key? W and X. So R1, the first decomposed table is W and X. Now, if we get W and X, we can get Y also, as it does not violate my condition of the 2NF, that is Wx determines Y. It is a fully functionally, Y is fully functionally dependent on Wx, so we can include Y over here, but we cannot include Z because this Wx determines Z will violate my condition of 2NF. So the next decomposition will be done depending on the functional dependency which is violating my condition of 2NF. So this is the functional dependency for which my condition of 2NF is violated. So we need to consider the attribute present in this functional dependency to create my next relation from the decomposing the R. So we are going to get Z. So here X is my candidate key, W and X is my candidate key, and the functional dependency present over here is Wx determines Y and here X determines Z. Clear? So you can see that all the non-prime attribute in R1, that is Y, is fully functionally dependent on the candidate key Wx. Similarly, in R2, the non-prime attribute Z is fully functionally dependent on the candidate key. So in R2, the non-prime attribute Z is fully functionally dependent on the candidate key, that is X for R2. Let us take another example. Here there are 5 attributes in R, A, B, C, D and E. The functional dependency is given by AB determines C and D determines E. Here you can see that the essential attribute is obviously A, B and D. So the closure of ABD will give me AB, and from AB we are going to get C, and D is giving me E. So closure of ABD is the total relation. So ABD is my candidate key. So here the prime attributes are A, B and D, and the non-prime attributes are C and E. The functional dependencies are AB determines C and D determines E. So no non-prime attribute is fully functionally dependent on the candidate key A, B, D, because here there no D is present, here no AB is present. So it is a partial functional dependency as well as this is a partial functional dependency. As this is going to cause me a problem in 2NF, as this functional dependency is violating the condition of 2NF, so we need to decompose the R into its 2NF form. So after decomposition, first relation will be on the considering the candidate key, that is A, B and D. Then the second relation will be on the functional dependency which is violating my condition of 2NF, that is considering AB, and we are going to get C, and the third one will be D and E. So here the functional dependency, there is no functional dependency, so we don't need to consider it. Here we are having AB determines C, where the non-prime attribute C is fully functionally dependent on the candidate key AB. And here we have D determines E, where the non-prime attribute C E is fully functionally dependent on D. So after decomposition, we are going to get these three relations. Now consider this example where R is a relation of A, B, C, D, E, and the functional dependency is given by set of the functional dependency is given by AB determines C, C determines D, and D determines E. Now the essential attribute is obviously AB, and AB closure is going to give me C. From C we are going to get D, and from D we are going to get E. So AB closure will give me all the attributes. So we can say that AB is the candidate key. The prime attributes are A and B, and the non-prime attributes are C, D, and E. Now the functional dependency AB determines C. You can see that this is a fully functionally dependent. Now what about D and E? As AB determines C, we can say that AB determines D using the transitive rule. Now, as AB determines C and C determines D and D determines E, we can write AB determines E also using the same transitive rule. Now, removing any attribute from here, functional dependency AB determines D will not hold, or removing A or B from here, any one of the A or B from here, the AB determines E, that functional dependency will not hold. You can see that every non-prime attribute, that is C, D, and E, are fully functionally dependent on the candidate key AB, right? So we can say that the relation R is in 2NF. So there is no need to decompose it. So we are having transitive functional dependencies, but the non-prime attributes C, D, E are fully functionally dependent on AB. Next, analyzing this relation ABCD on the attribute ABCDE, and the functional dependency AB determines C, CD determines E, and D determines B. You can see that A is the essential attribute. So each and every candidate key should have A with it. Now, is A closure is enough to determine all the attribute? No. So if we add B to it, what attribute we can get? We can get AB determines C, so we can get ABC, but we cannot get D or E. Now, if we add D to, if we consider ABD, then that closure will give me AB, C, and from CD we are going to get E. So ABD is going to give me all the attributes. So ABD can be a potential candidate key. And remember, neither AB nor AD is a candidate key. So ABD will be my candidate key. Similarly, if we consider A with C, then we are going to get only AC. But if we include D within it, so we are going to get A, C, and from CD we are going to get E, and as we are getting D and E, so we are going to get B also. So A, C, D can be a potential candidate key, and AC is not a candidate key and AD is not a candidate key. So ACD is my candidate key, one of the candidate key. Similarly, analyzing ADE, we can see that A, D, and E will give me A, B. DE will give me B, and as we are getting AB, so we are also getting C. So ADE is also a candidate key. Here there are three candidate keys which are ABD, ADE, and ACD. The analyzation of this one, you can do it by yourself. So what are the prime attributes over here? Obviously, each and every attribute present in the A, B in the candidate key, that is AB, obviously C and D, and also E. So there are no attribute which is a non-prime attribute. And as of definition of 2NF, it says that each and every non-prime attribute in R is fully functionally dependent on the candidate key of R. As in this example, there is no non-prime attribute. Obviously, the relation R is in 2NF, because in 2NF we need to consider the fully functional dependency of the non-prime attribute. Here there is no non-prime attribute, so we do not need to consider anything. So the relation R is in 2NF. So that's it for today's video. In this video, we have learned about the normalization and different normal forms, and we have learned about the 1NF and the 2NF in details. Now, while giving the examples, we have in 2NF, we have assumed that all the relations are in 1NF, because by definition of 2NF, a relation can be in 2NF if and only if it is in 1NF. So we have assumed that all the relations we have considered over here are in 1NF. So thank you. See you in the next video when we are going to discuss the third normal form and the Boyce Codd normal form, or the BCNF.